Yeah. Yeah, before going to start Dr. Vishwanath lecture, I'm going to brief about introduction about Dr. Vishwanath. Dr. Viswanath Bijlawan is an assistant professor in computer science and artificial intelligence at SR University, Warangal, India. He previously served as a postdoctoral research fellow at the Intelligent Control and Robotic Systems Lab at the Hanbant National University, South Korea, and as an assistant professor and head of the Department of Electronics and Communication Engineering at the Institute of Technology, Gopeshwar, India. Dr. Bijlawan was recently awarded funding for a prestigious DAD artificial intelligence project and will begin his role as visiting scientist at Friedrich Alexander University, Erlangen, Newburgh, in April 2024. Earlier, from October 6 to October 12, 2024, he visited the Mission Intelligence and Data Analytics Lab at FAU Erlangen when he collaborated on cutting-edge research initiatives. With over 12 years of teaching experience and a year in the industry, Dr. Bijlawan is an accomplished researcher and educator in the field of computer vision, soft robotics, shape memory analysis activator, human gait analysis, human activity recognition, and deep learning. He has published 23 SCI indexed papers, including contributions to prestigious IEEE Transaction Journal. Dr. Bijlawan serves as an editorial board member for leading Q1 journals such as Industrial Robot and the International Journal of Interactive Multimedia and Artificial Intelligence. He has also edited several books and conference proceedings, further contributing to the dissemination of innovative research. Dr. Bijlawan is a senior member of IEEE and he is actively engaged in Region 10 activities and is a member of IEEE Robotics and Automation Society. He has chaired numerous international symposia and conferences fostering global collaboration in advanced research. In the past, Dr. Bijlawan held the position of TechCube coordinator, where his leadership significantly contributed to his institute being recognized as a top performer in the program. His accolades include in 2021 Uttarakhand State's Government Excellence Award for Research and prestigious 2024 DAD Artificial Intelligence Net Postdoctoral Fellowship awarded by Germany. Dr. Bijlawan dedication to advancing AI and robotics continues to shape innovations and inspire young researchers in these domains. This is about Dr. Vishwanath Bijlawan. You can think about that university where he has done recently postdoc, that handbot research in South Korea. And 2 days back, we have one keynote speaker, Dr. Eng Shin Kim. He worked under Dr. Eng Shin Kim. And I know him, Dr. Vishwanath, for a long period. I think he's a very good researcher. He's working in one of my friend. He's colleague with both are working. And now I'm going to hand over the mic to Vishwanath. Vishwanath, please start your presentation.
Okay, okay, Professor. Thank you so much. Thank you so much for this
Yeah,
wonderful
yeah. Thank you, thank
introduction.
you,
So,
thank you, thank you
okay,
for accepting our
so
request.
yeah, Professor.
Yeah.
So, okay, so is my slides are visible, Professor?
Yes, yes, yes. Visible,
It is
Vishwanath.
moving also. It is moving
Yeah, yeah,
also.
yeah, yes, 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 yes.
Okay, Professor. So, okay, very good evening to one and all. Okay, so as a Professor already introduced me, I am Dr. Viswanath Bijlawan, Assistant Professor of Computer Science and Artificial Intelligence at SR University, Warangal, India. So before this, during 2022 and 23, I was postdoctoral fellow in Intelligent Control and Robotics System Lab at Hanbart National University, South Korea. I was this year I was also selected as a DAT AI Net Fellowship. I got. Okay, so today's my talk will be focused on safe memory alloy-based robotic actuators and their novel design. So basically, I will focus on some novel design of which we develop in our lab, novel design, then modeling and control through advanced artificial intelligence algorithm like deep learning and reinforcement learning and advanced transformer-based architectures and their control strategy. So the talk outline is will be as follows. In the first part, I will talk about SMA. Then I'm going to show you some novel designs of SMA robots which we developed in our lab, and then finally I will talk about some novel, some advanced artificial intelligence control algorithm. So okay, so something I would like to highlight, although 1.5 hours is not sufficient for that, but okay, I will try to cover up as many things as I can. And I will also introduce, I will give also introduce some my research topic also. So some significant area where I am working nowadays. So some slides also include this one. So okay, so as you know that this is a introduction to safe memory alloy. So this is basically a smart material which nowadays which is very useful in robotics and automation. So you can see here the things like materials with the help of this material we built some this rover tires. Okay, so what is this? First of all, the question is what is this and how it is going to useful for our research. Okay, so it's a uh, uh, okay, so as the name itself speaks that if any changes are there in the shape, that can be now memorized by these alloys. Okay, and whenever like during the reverse effect or during the unloading effect, they can be reframed into their original size or shape without putting any external effects. Okay, so basically it's a smart material which is having the memory effect. Okay, basically it is we are able to once it is going to deform, then we are able to regain its shape and size again. So this kind of property it possesses, that's why it's known as memory alloy, shape memory alloy. Okay, so okay, shape memory alloy exhibit memorical features with common mechanical properties of the material. If such alloys are plastically deformed, and these material at one temperature, they will be completely recovered to their original shape when they are being raised to a higher temperature. Okay, so whenever we are going to change the temperature, uh, first we are going to deform, and when we are going to change the temperature. So basically based on two phases, austenite and martensite, we are going to recover this uh, original shape. So that is the beauty, and that is the uh, importance of this SMA material. Okay, so with the help of this SMA material, we are going to make several actuators in the uh, in the lab. Okay, so basically composed of metals such as nickel and titanium, and this shape memory effect is a result of the material's ability to undergo a reversible solid state phase transformation. So basically it consists of two phase. Okay, so these are some application area where we can use deformable wings, then crawling robots, then bionic dragonfly, then stunts. So stunts in like those patient who go undergoes to the uh, surgery, bypass surgery. So we can put with the help of SMA material, we can make stents, and we can insert those stents in the patient artery, so that it will be okay. So for the heart patient, it is a boon. Okay, so other areas also. So okay, so basically this SMA consists of two phase, austenite and martensite. So okay, so basically austenite is a high temperature phase, and martensite is a low temperature phase. Okay, so once you see this austenite phase, so the crystal lattice are symmetrically and cubically crystalline and arranged systematically. When you see this uh, um, martensite phase, so it is little bit twinned. Okay, so twinned structure is there, and also there is one more martensite state, which we call it t-twin martensite. Okay, so in recovering their shape, the alloys can produce a displacement or a force as a function of this. Okay, so for example, how we can use this? Okay, so we are having SMA wires, and we can make several actuators, and with the help different design we can make. And okay, so once it is deformed, and once we are giving the heat, or maybe we are giving some electric current, so it is going to regain its shape. So while recovering their shape, the alloys can produce a displacement or a force, okay, as a function of temperature. Okay, so basically in alloys we can say that combination of both really feasible and possible, where mechanical strength and shape memory effect can be added together. Okay, so we can make a metal change, like change in the shape, change in the position, pull, compress, expand, bend, and turn with the heat, just as the only activator. Okay, so with the help of this phase, okay, so here you can see here, this is three states of this is the states phases of SMA. So austenite, which is when we heat the SMA material, and when it is going to cool, then it is going to return its twinned martensite states. And if we do some loading effect, then it is going to detwinned martensite. Okay, so this is the phases, basically two phases of SMA. Okay, so you can understand the functioning of SMA here. Martensite, okay, for example, initially at the lower temperature, the if we take a iron, if we take a SMA rod or something, okay, so if we are going to deform it, so it is second stage is deforming martensite. Okay, so once we reach in deformed martensite, and again we are going to heat it, so we will reach in austenite. So basically it is going to recover its shape. Basically it is going to recover its shape. So initially the SMA material, SMA actuator or something is in their original positions. Okay, so if we are going to deform with the help of some stress or strain, okay, so we are achieving that state, then again we can with the help of heating effect or some external electric current, we can it can recover its original shape, austenite. And once it is cooled, then it is going to recover reach again its in original form, that is martens. Okay, you can see here the this diagram. So MF is the martensite, full martensite states. Basically, this x-axis is temperature axis and the y-axis is crystalline arrangement. Okay, so MF is a martensite, full martensite, then MI is the initial martensite. Okay, so in the similar manner, AI is the initial austenite and AF is the final austenite. So as the temperature increases, we are going to austenite phase, and as the temperature is going to reduce, we are going to achieve in the martensite phase. Okay, so it can be classified. Shape memory effect can be classified into two ways. So one is one way shape memory effect. Okay, so initially you can see here in the diagram uh, a position A, then position B, C, and D. So once martensite means in the low temperature phase, so once it is going to deform, and again, okay, once we deform it, and again if we are going to heat it, then we are going to achieve austenite phase. And again if we going to reduce again this temperature, so we are going to reach in martensite uh, states. Okay, so this is one way, only one way uh, uh, shape change. And on the other side, two-way shape change. So suppose one initially it is in martensite phase A, and okay, so it's a martensite phase A. Then if we are going to deform it. So B is the deformed state. So okay, so C and D are the two different states. So we can uh, reach by C to D, and in the similar manner we are going to reach from D to C. So there is no option to reach in again in the martensite states. So here basically in the C state we are going to train the SMA, and D states it is going to reach in austenite phase. So it is unachievable to reach again in martensite. Okay, so basically here two states will be remembered, that is C and D only. Okay, so as per the definition, the two-way shape memory effect is a phenomenon in which the reversible spontaneous shape change during heating and cooling occur without any external stress. Okay, so like that. So now we will talk about hysteresis. So basically, this safe memory alive material shows the hysteresis effect. So hysteresis now, if we talk about hysteresis, so once we are going to, okay, here in y-axis, if you can see martensite phase fractions, and this is temperature axis. Okay, so like that we MF and M start, martensite phase start, and AS means austenite phase start, and AF means austenite phase final. Okay, so whenever we are going to heat this one SMA material, so we are going to reach from the above curve, you can see hysteresis. It is going, you see this heating curve from, okay, so 1 is 100% martensite and 0 means 0% martensite phase. Okay, so one from one state to another state, you can see here it follow a non-linear kind of trajectory. Okay, so we are not following in the linear relationship. So whenever we are going to heat it, so it follow this trajectory. Okay, so non-linear dynamics, total non-linear dynamics. Okay, so we will reach from martensite phase to austenite phase. Okay, and once we reach austenite phase, then if we are going to cool it, this SMA material again, so it will follow, it will not follow the same path, and it will follow the another path. Okay, so uh, you can see the trajectory here. AF to MS, up to MS is almost 0% martensite. Okay, so from MS it will start. Okay, you can see here MS, it will start martensite phase again, cooling phase again, and then we are going to reach once at 100% martensite. So this is in the this SMA follow the non-linear hysteresis curve during heating and cooling. So this is most important. Why? Because when we are going to uh, model the our SMA, so that time this is a real difficult to model this SMA, because it is not having the linear kind of relationship. So that time it is very difficult to model it simply. Okay, so that's why modeling itself, modeling SMA itself is a challenging task. Okay, so there are several models, proposed Brinson model and several other models of which we also gone through those models, but those are not effective at all for SMAs. Okay, so one more property is SMA is having, that is known as super elasticity or pseudo elasticity. So okay, so here you can see the diagram load, y-axis is load and the x-axis is temperature. So you can see here MF means martensite phase full, MS means martensite phase starting, then AS means austenite phase starting, then AF is austenite phase full. So in that case, when we are going, when we are giving the loading effect to the SMA, this in this condition we are not hitting it, and we are giving the loading. Okay, so at particular temperature we are going to okay, definitely we are giving the load effect more than AF. You can see here AF is a austenite phase, and austenite phase is a high temperature phase. So when we are giving this loading effect to the SMA material, so it is going through all the uh, transition, going through the AS. You can see it is bisecting this AS curve, then it is also cutting this MS curve, and then if we will go, if we will give more loading effect, it will also touch to the MF martensite phase. So basically phase changes from austenite to martensite, and then again okay, so it will not follow the same path, and again it will come from the different path. Okay, so like in your second diagram, you can see here when stress and strain curve we make, so 0 to A, then A to B, then B to C, and then okay, so if it reaches to the martensite C state, then it is coming back to the without unloading effect. So with the unloading effect, it is following the different path and reaching to the again the initial state. Okay, so this property makes this is a super elasticity property, and in this okay, so this property is ideal for the application where the high flexibility is required, like biomedical devices and aerospace engineering. So biomedical devices means, suppose we are making some braces of the uh, human dental orthodontic treatment, like nowadays, which is very common in the fashion. Okay, so for treatment of your dental things, okay, I will show you. Okay, so very common in the so there we can use this as a, this material we can use for the braces and other area also. Okay, so also nowadays smart this specs also we can make this with the help of this SMA. Okay, so in this you can see here pseudoelasticity and shape memory effect. Okay, so both are two different phenomena which is exist in the shape memory alike. So in pseudoelasticity, basically we are having, first phase we are having one Okay, so in initial state it is like this. Okay, you can see here in the diagram the first state 1, 2, and 3. So we are giving some deformation. Okay, so with the help of some loading effect, we are making it deform, and once we are leaving it, it is going to reach its in uh, uh, original positions. Okay, martensite phase. But here uh, okay, so here initially uh, because okay, so in the previous curve you see this, we are doing this in the austenite phase. On the other side, in the shape memory effect, if original is at low temperature, it's austenite martensite phase, then we are going to deform. uh, okay, so with the bending, if we are making it bent, then okay, so then it is going to, and if we are heating this uh, element again, so it is going to recover its phase. So basically this after bend, this third one is its austenite phase. And if after austenite phase, it is, if we make it cool, so it is going to reach its martensite phase again. So this is two different phenomena. One where one in one pseudo elasticity, it is because it's having the property to highly elastic, so it is going to regain its shape, and on the other side it is going to regain its shape with the help of the some external current source or external temperature. So okay, so now the question is how we can use this SMA effect. Okay, so we know a little bit something about this SMA. Okay, so for example, if we are having a spring here, we can make it deform, and once we are going to heat this spring, so it is going to take one motion. Maybe in this case, as per the figure you can see here, so it is going to make a motion in upward direction. So okay, initially at 20 degrees centigrade, the okay, so we make it deformed with the weight at 20 degrees centigrade. So it is like this, spring is like this, and once we are going to heat this maybe 100 degrees centigrade, at that moment it is going to recover its phase. Recover its shape. Okay, so when it is going to recover its shape, in that motion, in that process, it is going to, we are having one force. Okay, so we are having some force and displacement also. So we can use this smart property for our uh, actuation actuation, making a smart actuator based on this property. Okay, so you can see here initially 20 degrees it is elongated, and once we are giving its some heat or something, okay, or some electric current also, both can work. Okay, so in that case it is going to regain its shape. Okay, so at 100, so while it is going to regain its shape, it is making some motion. So we can use this motion, this force, this displacement for our actuation methods in by in several robot, like robot, we can make robotic hand, artificial muscle we can make with the help of this property, because initially we can elongate, and once we are giving the force, once we are giving them heating methods or some electric current, and it is going to contract. So in that it is we are having several motion, some linear motion or different, based on the design of the actuator. We can use different motion, we can generate different, like we can twisted motion also we can. So in order to get twisted motion, we need to design our SMA in such a manner so that we are getting that twisted motion also. Okay, so like this. Okay, so application of SMA. So nitinol is used in medicine for stunts. Okay, so as I told you initially, this is a human artery is there, and initially uh, we close this, we make the this stent with the help of SMA stent, and okay, we are going to insert inside the human artery. So you can see the plaque level here also, and okay, initially, so inside this, once it is contracted, we insert this inside the human artery. Then we are having some balloons inside this SMA wire, SMA stent, and we are going to open this balloon, and it is going to expand. So you see how this is doing the bypassing, how it is going to expand the human artery. And once it is going to uh, 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 okay, once it is going to expand, then you can see the compressed plaque is there. So it is basically the procedure of bypass surgery in the human artery. So this, with the help of this smart material SMA, we can make this use of this uh, smart stunt made up of SMA. Okay, so we can use this structure also. So all these procedure, we can make a novel design based on SMA, and we can control uh, with the help of control algorithm. So nowadays, as I told you, that controlling action is required, because this SMA follows the uh, hysteresis kind of hysteresis curve. Okay, so it follows the hysteresis curve. So to control this SMA is little bit complicated. So that's why earlier control strategies like PID control or neural network control or some are going to fail in this. So we for controlling action of this SMA, we require some advanced control algorithm. Okay, so adaptive, maybe neural network kind of control for. Okay, so we will discuss that. Okay, so these are some application area of SMA. Okay, so stents are there. Okay, so braces are there. Then biomedical MIS, this robotic hand, we can make a soft gripper based on this SMA properties. As I told you, it is having uh, okay, so initially, with the help of this motion which we saw in the previous slides, so it is going to, when it is going to recover its, okay, suppose for example we are having some SMA material, we are making some different shape, and we are going to deform it, and once we are giving the some electric current or some uh, heating this SMA material again, so it is going to recover its original shape. So while recovering its original shape, it is giving us some motion, some one dimensional motion, or maybe two dimensional motion based on our design. So basically, while we are doing the research, in the research point of view, when we are doing the research, so we can use this property of, while regaining its original structure, it is giving us some motions. Okay, so with the help of those motions, so we can make several uh, uh, application of this uh, SMA, so biomimetic autonomous underwater vehicle. So okay, so some those I also saw some examples like uh, where the robotic fish scientists made some robotic fish based on SMA material. So it is without any external power. Initially we have to trigger it, and once it is started, it is going to heat and cool automatically. Once it is going to, so it is going to face transformation by itself, and it is a continuous kind of things. Okay, exoskeleton muscle, most important use of this uh, SMA material is exoskeleton artificial muscle. So in our research, we can make exosuit. Already we made some exosuit in our lab also. I will show in the subsequent slides those novel designs. And exoskeleton muscles also, artificial muscle, we can make it with the help of this SMA wires and SMA materials. Okay, so these are some basically some okay, so some use application of SMA materials. Okay, so these are some, like you can see here, eyeglass frame. Okay, so we can, if we can do it, we can make it we can we can deform the shape of the eyeglass frame, and it is going to regain its shape. So where this kind of property we can use in several uh, places, several application also. Okay, morphing wings, where the material changes its shape in response to aerodynamic conditions, enhancing aircraft performance. Or so aircraft wings also we are making with the help of SMAs, via SMA materials. And we are going to use. I also saw that NASA also made uh, some tires based on SMA materials. Okay, so initially I saw shown this nitinol based arrangement of SMA wires. So you can see here, while moving, while going in the uneven terrain, that time this SMA material is going to deform. Okay, so when we are not having the smooth roads or smooth surface, or we are having the uneven terrains, so that time this SMA materials is going to deform. But as you know that with the help of heating effect or control, with the help of some current or okay, so it is going to regain its shape. So it is very useful in the uh, maybe space exploration missions also. Okay, so where there is a need of uh, like those kind of robust tires where we can use in those kind of scenario. Okay, so now one more application area where we can use is micro valves. Okay, so micro valves you can see here. Initially this nitinol, you can see this black A figure and B figure. So first figure is the valve is off state. So in the nitinol actuator is deformed shape. So okay, so as I told you, we can we want to use this motion. So we are going to heat this nitinol actuator, and once it is heated, it is opening this valve. So on state is also okay, so on state is there. So we can use this thermal valves or micro electromechanical system valve also in laptops or computers, where they're automatic. We can use we can build also some SMA application in the uh, self-adaptive, we can say it self-adaptive micro valves in system, in computer system also, because you know our systems, those are bulky system and high computational power, they are going to heat. Okay, so after certain time, can we make some kind of system with the help of SMA wires, okay, SMA materials, so that once it is heated up to certain temperature, it is going to change its shape and opening the micro valves. Okay, so all the heat is going to exchange with the environment. Okay, so with this kind of systems we can make with the help of nitinol, we call it nitinol, okay, and nickel titanium actuators, or nitinol or SMA shape memory alloy. Okay, so as I already told you, as used in the robotics to create artificial muscles and joints. Okay, so more allowing for more natural movements. So whenever we want some different kind of motions or natural movements, so all the, as you know that different in robots, there in robotics there are different kind of actuators, but pneumatic actuator and other actuators, but those actuators are sometimes having some constraint. But with the help of this nitinol wires, we can generate any kind of motion. So that will be our novelty in our research. Okay, so we can generate different kind of natural human like movements with the help of this nitinol SMA. Okay, and one more thing, the biggest advantage of this nitinol SMA or nitinol wires or materials is that it is human friendly. It is having the high degree of biocompatibility. Okay, so we can, it is always compatible with the human body. Okay, so smart textile in okay, so we can make some smart clothes also. Okay, so many in the many, so 360 degree we can use the property of this nitinol, and we can use this property of nitinol, and we can make several application based on this smart material, this shape memory alloy. Okay, so what are the advantages of this SMA is high level of strength, excellent fatigue resistance, and corrosion resistance. So basically, it is biocompatible, which I already told you, and diverse field of. Okay, so this is the, okay, so corrosion resistance means, okay, so that's why it is a corrosion resistance. That's why it is used in the biocompatibility and human. Uh, okay, human in we can use with humans or animals the some actuators or some design. Okay, so that's why. Okay, so good mechanical strength also. And disadvantages, okay, so disadvantage is expensive material. Okay, so this very expensive, and it is having poor fatigue properties and over stress. So these are some disadvantage of the shape memory alloy materials. Okay, so you can see here in detail. So advantage is also wear resistance, then fatigue resistance, then super elasticity, easy fabrication, high power to weight ratio, then lightweight, then biocompatibility. And a disadvantage when we talk initial investment, so that's why it is highly um, it's a costly. Okay, and sensitive fabrications, residual stress also. And one more thing, that non-linearity problem, non-linear actuation force, it is giving non-linear. Okay, so control requires a huge effort for controlling the shape memory alloy actuators or shape memory alloy based systems. Okay, so lower maximum frequency of actuators. Okay, so challenges. Okay, so due to the complexity of the manufacturing process and the specific alloy composition required. Okay, so that these are some challenges. Transformation temperature range may limit the operating conditions of SMA based devices. So temperature range limit the operating condition of SMA based devices. Okay, so response time can be relieved. Sometimes we require high response time. So okay, so whenever I worked with this SMA actuators and uh, so with the help of these devices, when I am deforming it or transition from one phase to another phase, it is going to easily deform. But when we are going to recover that shape, so that when we are finding that actuation force or getting that actuation force, so sometime it is non-linear. First of all, it is initially very slow, then suddenly very high. So controlling action is required. That is also difficult. And one more thing, this is uneven response time. So you have to, this is the major drawback of SMA. So you have to think uh, some some external cooling mechanism for while recovering its phase, so that it can have a linear kind of motion, or sometime it is also slow, initially slow, and then suddenly it's going to recover that from that shape. So that kind of actuation mechanism is also a challenge for and limitation. Okay, so in the future trends, uh, okay, so we can make some several design and prototypes based on this SMA. Okay, so micro stents and cardiovascular application and orthodontic application, which I already mentioned earlier. So, okay, so in this integration of SMA with other smart materials such as SMA polymers open up new possibility of multifunctional materials. Okay, so that is the some advanced future trends. Okay, so fascinating area. So it's it possesses two properties: safe memory effect and super elasticity. On also helpful in the biomedicine, aerospace, robotics, and automotive, and continues the potential. Okay, so technological advancement, definitely we are going to make several designs in futures with the help of SMA material. Okay, so now I will share my uh, our designs, our lab designs, which our friends and me together made those in the lab. So okay, so initially, okay, so this is one our first design. So this is basically a caterpillar robot. Okay, so basically we use okay, so this we use in this we use SMA springs, four SMA springs. So you can see here SMA1, SMA2, SMA3 as an antagonistic approach. And okay, so find tracking the motion of this uh, inching and crawling robot, we use in inertial memory, IMUs, inertial memory unit, which consists of accelerometer, gyroscope, and magnetometer, three axial accelerometer, gyroscope, omega x, omega y, omega z, and angular that magnetometer also. So three axial accelerometer, gyroscope, and magnetometer. So basically for finding the motion of the inching, okay, and it basically perform the inching, crawling, and undulating motions. Okay, so in this design, we with the help of SMA spring, we made this motions possible. So okay, so you can read this like antagonistic of configuration and clockwise and counterclockwise motion. Also a front and rear legs with the claws are designed. So you can see here design of the claws in arc shaped claws. You can see here in the diagram, second picture, you can see this arc shape design. And okay, so three inching and two crawling locomotions, basically it provides, and total six locomotion strategies in the bang control structure. So you can see here this inching and crawling motions here. So step one, then transition, then step two. Okay, so this is the basically design, and like a motion of caterpillar, how caterpillar is going to walk. So in the similar manner, this this actuators, this caterpillar robot is going to walk, and it is giving us six different locomotion strategies: crawling, inching, and undulation motions. Okay, so like this. Okay, so we will not discuss this too much. Okay, so we also calculated the times for 0 second, then 9 second, then 16 second, then 25 second. So how you can see here, phase one, then phase this is second, after 9 second it's like this, then 16 second, then 25 second, then so different motions it is going to do. Okay, so will not. Now the second design is based on the robotic hand design. So okay, so we use uh, some PCBs, okay, and with the help of, we needed some with the help of some specific wire diameter we use for our for this robotic hand operations. Okay, so we made this with the help of you can see here this arc shape as arc shape SMA with the help it is joined in the two PCBs, two different PCBs. Okay, so we want to generate the hand motion with the help of this with the help of this SMA wires. Okay, so we built our we built our actuators. Okay, so DIP joint and PIP joint. You can see here different joints are there. Okay, so okay, I will show you the design. Okay, so this is the basically robotic hand. So okay, so three joints are there: TIP joint, then PIP. Okay, so similar look to a robotic hand, like okay, basically everything is from nature inspired. Okay, so we want to mimic the human motions of hand in the similar manner. If we also made some knee angle knee joints or knee joint and knee actuators, and those are going to mimic the human motions also. Okay, so knee of the knee joints. So here we made this for the mimicking the human hand motions. So in human fingers there are three types of joints are there. This is DIP, PIP and MCP joints. So basically we will do the flexion and extension motion, flexion and extension motion. Okay, so like that this we designed the uh, these are nothing but the soldering uh, not soldering, we knitted every joint, we make every joint with the help of SMA wire, and in the arc shape we made it, and backside we made that this polyamide tape and some rubber we used for okay, so some action. Okay, so and this is the control setup for controlling the robotic hand. So basically we used first microcontroller. Initially we used Arduino based board, but that is not sufficient for why, because when we are going to integrate the artificial AI advanced AI algorithm, so that Arduino fails on that kind of systems. So we required NVIDIA device, which is basically microcontroller, advanced microcontroller, and having the capability of all the in this AI algorithm capability to run all the AI algorithms, deep learning framework, and reinforcement learning. So for those kind of algorithm, we require some advanced microcontroller. So that is basically Jetson Nano device. So our Jetson Nano device is a microcontroller here. Then we use this IMU sensors. Okay, so it consists of this, you can, okay, so different pins are there: VCC, ground, SCL, SDA, XCL, INT, like that. Then we use pulse width modulation driver circuit. So I think had had driver had I forget, I had mod 16 driver, I think, PWM driver, then SM actuator. Basically this is SM actuator, our SM actuator. So this is the complete setup of how we are going to control this robotic hand with the help of microcontroller and sensors. So we integrated also for measuring the acceleration and positions value, because if we are having the acceleration value ax, ay, az. So with the help of ax, ay, az, suppose my hand is moving, doing like this kind of motion, grasping motion, and then flexion extension motions. In that motions we are having uh, continuous value of acceleration and gyroscope and magnetometer, mx, omega x, omega y, omega z, and mx y, mx, my, and mz. So if we are having ax, ay, az, so with the help of, okay, so there are the methods, inverse kinematic methods. So we can, with the help of inverse kinematic, we can find out the joint angles which are involved in this robotics hand motions. So once we, with the help of inverse kinematic, we can find those inverse joint angles And once we are having joint angles, so we can make our analysis, advanced analysis of our robotic hand based on those joint angles. So these are some motions. mm, okay, so which we tested our robotic hand for the different scenario. So grasping of disc, circular use of CD disc, and grasping of X also. So grasping of different objects in the lab. Okay, so large diameter objects and small. We tested with different scenario basically. So uh, grasping of egg is one of the difficult task, and we perform this grasping of egg is in our lab. So our robotic hand is robust robotic hand with the made up of shape memory materials. Okay, you can see here it is holding the pen also. So okay, so like that, different we tested for different like here. So it tested for different scenarios we have. Okay, so grasping of egg. Okay, so at rotation and it also rotated the eggs in different motions. Okay, to translation motion and rotation motion also. Okay, so like that, you can see this grasping of egg in the lab. We perform this. Okay, so basically three in this while making this robotic hand, we are a little bit concerned about this thumb. So with the different design, we somehow we are able to make this, because all the four fingers are similar, but while we are going to mimic this the hand motion, this thumb motion, so it is very difficult to find out this thumb. So it's really difficult task while designing this kind of systems in the lab. So very with a huge effort and very dedication, we are able to make this. So now I would like to show you how the design of this robotic hand we made in the just a quick okay, so you can see here motion. Okay, so we tested for lifting the different weights in the 255 gram also can, that's soda can or some cold drink can in the lab. Okay, so these are some different processes which involve while making the robotic finger. Okay, so basically we make one joint and bidirectional SMA also, and we can make it bidirectional as well as unidirectional as actuators. So so this is one design. So we can test for the different twisting motion also. We can generate twisting motion also, and different design and all that. Okay, so this is how it is assembled in the lab. Okay, so these are some minor details. So so you can see here DIP, PIP joint, all joints are in actions. So how we are controlling with the help of microcontrollers. So especially designing this thumb part is very difficult. So it's required huge effort for designing the thumb, because we developed actuators, unidirectional and bidirectional, both in our lab, but that was not capable. Okay, so like this. Okay, so this arc shape SMA, shape memory alloy actuators. Okay, so we, uh, we are making with the help of, we also elastic rubbers also we use in for getting the motion also. Okay, so this is this is arc shapes SMA, shape memory actuators. Okay, so now when controlling with the head of integrals sliding mode controller. Okay, so these are some how we apply the trajectory. Okay, so here we cannot show all the things, but this is the basic flow diagram of ISMC controller on the SMA actuators. So reference trajectory, then ISMC. Okay, so then actuator output, then end state observer we applied, and then we get the reference. So here we find out the trajectory, desired trajectory, and measured trajectory of the angles with the help of PID control. Okay, so PID control we applied. Okay, so while developing the controllers for the SMA, this bidirectional actuators, so I found that NARMX model and this adaptive neural network based controller are the best up to date. Now, even nowadays, new type of controller also came in the existence, and now the advanced research is mainly focused on the in this AI. Now the transformer models came. So advanced controller scientists are making the advanced controller based on the transformer models. So this kind of you make a design based on SMA, then you model it, and while controlling you apply the advanced controllers. So when I was in my lab in South Korea, that time deep learning and reinforcement learning based controllers are there, but after that nowadays advanced controllers came in the existence, and those who are able to apply those advanced controllers, definitely their paper will be accepted in the high level transaction. So you can see here this architecture of rotating SMA actuators and thermal mechanical states. Okay, so SMA links are there. Okay, two links are there. This is radius of curvature RC, and then this is the theta angle. So while hitting, it is going to change, and then cooling. Okay, so then we are getting the mechanical deformation also. So phase changes between martensite and austenites. Okay, so like that. Okay, so this is the design basically. Okay, this is another design of in some cases we are using polyamide tape for thermal resistance where the heat is very high. Why? Because sometimes it is not possible with a simple wire, so that you need to save your wires also. So in that case you need to require some thermal resistance wire, amide polyamide tapes or something to protect your IMU as well as your other connections also, because in this process the heat is also going to develop. Okay, so this is the again experimental setup for the how the Jetson Nano is connected to PWM driver and the actuators and actuator with the help of uh, actuator and IMU is attached to that, and we are getting it's okay. So this is one another design. So now one more design. This is basically tensegrity based design. So you can see here it's basically initially we made this it can move in back and forth and left and right and all 360 degrees. So not 360 when it's 180 degree on initially. So basically we made this design for the robotic eye motions. Okay, so robotic eye motion you can see here all SMAs are one how we made this design you can see here. Okay, so like this tensegrity uh, actuators. Now this is one more interesting design. So earlier designs are here in these design earlier designs. So SMA wires are open. So but as you know that when we are going to make a biocompatible design for the human maybe human knee joint or ankle joint or maybe hand motions, or so there we require some material which is which should be compatible to the bio. So okay, SMA is biocompatible, but sometimes it is heated in the heated position, so it's warm, so we cannot directly apply those SMA to our body in that case. So we can make silicon tube based design. So SMA basically inserted inside the silicon tube. Okay, so as okay, so this is one different design. Basically SMA is inside this silicon tube, and okay, so this design is also nature inspired. So basically this is lung what we call it uh, amphibian lungs. Okay, so amphibian lungs is design is having this kind of a structure. So okay, so okay, why we tested this kind of design? So okay, so initially we made different designs based on the SMA wires, so twisted design or something, as you already said, tensegrity design, then bidirectional, then unidirectional SMA. Okay, different design we tested. So in this process, uh, I want I want to make some artificial muscles for human motion, hand motion. So in that case, we require that kind of arrangement, that kind of setup, that kind of design, which will give us maximum force, which will give us maximum force. So we are testing in different scenario, different designs. Okay, so some are giving us some some good level of actuation, some good level of force, but some designs are not giving us proper force which we require for the opening and closing of this artificial muscle. Okay, so in that case, we tested different scenarios. So initially we made different designs. So after that, I we came to this design finally, and this is basically inspired from the amphibian lungs design. So this is amphibian lungs design, and we so it's very complicated process in the lab when we are going to design this kind of design. So initially, with the help of SMA wires, you can see here we are making bindings. Okay, so very difficult by with the hand only. There is no machine for making this. Okay, maybe machine will be there, but not available in our lab. So we made with these kind of design with the hand motion. Then we are going to heat it. Okay, so we are going to, so as I told you now, so in the two shape memory, two-way shape memory alloy, it is going to remember two states. So basically we can train our SMA to spatial pattern. So initially this SMA comes with some wires, bundles of wires. Okay, so we can train, we can make these design with the help of okay, so different things, and we are going giving it a training so that it will remember its original shape. Okay, so now the once we make it windings like this, it will remember this winding. How it will remember? We are going to heat this in the autoclave at up to 250 degrees no more than 500 degrees centigrade. I remember 500 degrees centigrade, and okay, in the oven. And once it is getting training, so now the SMA remember its shape like this amphibian lungs shape. So we are giving its training. So whenever we are going to deform, okay, this structure, we are if we are going to elongate this SMA design. So it while heating, it is going to recover this shape again. Okay, so this is the second part where with the help with the temperature we are giving it some training, so it will remember its shape. So initially it come with the wire, so we are making some design, then we are going to heat this design up to 300 up to 500 degrees centigrade, and then it is going to remember this shape, this winding shape. And then we are going to elongate this, and okay, so we are testing for different forces. So while giving a current or temperature to this design, it is going to recover its shape, and while recovering its shape, as I told you, as it is giving us some motion. So that motion we were using as in actuation mechanism. So simple, same kind of motion I want to extend in my robotic hand motion. So this is basically in this second kind of design, it is totally biocompatible. So we can make artificial hand design with the help of this kind of silicon SMA, silicon tube SMA. So earlier the problem with this design, these are okay, so these are naked wires, so it can harm to the human body. It can harm to the human because it is when it heated up, it can harm to the human body. But this silicon covered SMA, it is okay, so it is not like you can see here load cells. Okay, so we are testing our force in the lab experiment. Okay, so with the help of Jetson and microcontroller, then motor driver, then actuator. Okay, so we attach to supply to uh, uh, this actuator, and then we are going to find out what force and what are the elongations. Okay, so with the help of this scale, we are going to measure and with the help of load cell, we are going to measure the force generated by this design. So in while dealing with the SMA based designs, you need to require some different make some different patterns, and then you need to test for different pattern for the finding the maximum force. Okay, so this pattern, this design we achieved in the lab also. Okay, so you can see another SMA, for example. So this is our lab experiment, rolling locomotions achieved in the uh, robotic SMA based. Okay, so rolling. We also developed some jumping and rolling robot also. So this is actually, so you can see it is climbing a slope. This design. Okay, so that's why I told you the response time and non-linear behavior of SMA is going to create a problem. So that's why this is challenging also. We also see thermal images of with the help of FLIR camera system. Okay, so you can see the thermal variability of SMA wires, where is the red color dots are highly heated, while this green color is less heated. So okay, so that is also thermal effect also. In some part it is going to highly heated positions, and some are less heated positions. Okay, so this is okay, so this is okay, so this is okay, so this is unidirectional motion rotation. Okay, so you can see thermal images also. This the motion back and forth motion achieved here. So bidirectional SMA, it's a basically bidirectional, in both directions it is going to move. So while dealing with this SMA based designs, you should always have thermal profile of SMA also, so that you can make a relationship of thermal with displacement and thermal temperature with displacement. So we are going to measure this thermal temperature with the heat sensor also. And this sometimes because of this non-linearity and this hysteresis, this slow reverse motion is little bit difficult and little bit challenging also. So uh, we dealt this kind of problem many times. So still we are struggling to find out the optimum solution for SMA hysteresis. Okay, so different test designs we tested in our labs. Okay, so this is the complete SMA. Okay, so SMA actuation method. So we have to follow these steps. So mechanical design, then finding the inverse kinematics, forward kinematics, then differential kinematics, then dynamics, then hardware design, then SMA actuation and instrumentation, then control design. Okay, sorry, the design spelling is mistaken, and testing and evaluation. So this is the complete flow diagram of SMA based systems. Okay, so this is one of the paper which was published in Sensors and Actuators in Q1 journal. Modeling and control and some novel bidirectional, which I shown you earlier. So bidirectional SMA actuator for soft robotic applications. So okay, so we made this design. Then okay, so this temperature variation, then modeling of so basically modeling also challenging of not because of that non-linear problem of SMA. Okay, so modeling is also difficult. So then still we model with the help of NARMEX and FROLS method. Then we applied some controllers, that basically PID and sliding mode and integral sliding mode controllers. Then robustness analysis by We also created some disturbance scenario. We inserted some disturbance in the system, and then we calculated its robustness of the controllers. So this is basically this all about. So this is one more design. So a small scale knee exoskeleton using safe memorialized springs. So for the knee exoskeleton, we made this design also for the knee joint. So you can see here, okay, so how it is attached to the both direction of the knee. Okay, so front side and back side also.
Outlines, introduction.
Okay, so we'll not discuss this too much. Okay, so just focusing on design. Okay, so this design, you can see here SMA springs we used. Okay, so you can see here uh, SMA spring supporting the biceps and the semitendon. Okay, so these are some medical terms for the bone joint of knee joint. Okay, so bicep femoris, and then so okay, basically group of bunch of wires of SMA, and we made this design. So I am
Conceptual design, figure 2.
not discussing this, and modeling with the help of standard constitutive model. Okay, so this is basically so okay, so how the temperature and martensite fraction and shear stress strain are related to. Okay, so transformation tensor, then tensor on G is the shear model. Okay, so we will not discuss this too much. So PID control modeling. Okay, so basically this design is with the help of this design. Okay, so this is this is the knee angle basically, and the theta desired versus theta actual, so which we got. Okay, so you can see the curve of knee joint here, 0 to 50 it moves, then again down, then okay, so desired was, and theta knee is different. Okay, so desired like this, and but it is almost able to uh, uh, capture those desired motions. Okay, so
Outlines,
this is second
introduction, linear actuator architecture.
this is second design. So okay, so linear actuators and mathematical modeling. Okay, so this is second design for the human uh, muscles joint. Okay, so basically it consists of pulley systems and the long SMA wires are with the, you can see here the design. Second part is SMA spring is also attached, and the three pulley system basically for the motion of the muscles. Okay, so tendon motion and antagonistic spring also we use for that. So okay, so this is one of the, no, you can see here fixed, first one is a fixed point, then second one is a pulley, then third one is axis perpendicular. Okay, so third point is a perpendicular design, then carbon filter tubes, then SMA wires, then okay, so here it is not possible to show you this design completely. Okay, so
Figure 4
this
shows
is
the PID control of the actuator position.
yeah.
Subfigure A, position in millimeter. We have the desired position as a step and the actual position. Subfigure B, control signal. Subfigure C, the temperature. In the beginning, there is heating, then there is natural cooling. As shown in this figure, the step position trajectory of 14 millimeter for 30 seconds is used. The input
So this is basically
is 24 volts.
Hmm.
And the controller gains are given below KB, KI, KD. Our experimental results in figure 4 shows that the
Okay, so this is basically novel node design. So now I will talk about uh, microcontrollers. So latest microcontrollers, Jetson Orin Nano. Okay, so recently, just I think 2 months back, it is launched by the NVIDIA. So basically, it's used for the highly okay. So if we are doing some robotics kind of experiments, in that experiment, what are the latest technologies? So this is the latest technology developed by NVIDIA. So Jetson Orin Nano is developed. So okay, so it is very useful for robotic control, then vision processing and deep learning based automation. And basically, if we want to see the generative AI nowadays, which is very famous and very popular, like GPT, generative pre-trained transformers, so GPT models. So those kind of things we can make a reality in based on this. Okay, so this is basically a, not, we cannot say, but we can say that this is a supercomputer for the edge computing devices. Okay, so supercomputer for the edge computing devices. Okay, so it supports transformer models, then LLMs and diffusion model for AI driven robotic applications, then real-time decision making for autonomous robots also, then high computational power at the edge. Okay, so 40 trillion operations per second AI performance it is giving us. So see how it is very fast neural network inference also. Okay, so deep learning models we can okay, so with the conventional Arduino and this Raspberry Pi, we are not able to run this advanced generative transformers architecture. So nowadays there is a novelty. If you are a control guy and if you want to control the robotic system with the help of advanced controllers, so advanced controller nowadays based on the transformer models. So if you are able to drive those transformer models, then you, so for computation. Okay, so now it comes to the computation power. So transformer models require high-end GPU system. So you can use this high computational power powered this Jetson Orin Nano. So only this is able to run your programs. Otherwise, you are not able to run your robotic systems. Okay, so for a independent researcher and roboticist, he should definitely purchase this Jetson Nano Orin Nano developer kit for himself. Okay, so Edge AI for low latency controls. Okay, so reduces dependency on cloud computing by performing AI inference on devices. It's crucial for autonomous robots, drones, and autonomous guided vehicles. The, why it is significant? Also, it is optimized for vision and sensor fusion. So, if you want to fuse some several sensor, multi-sensor fusions, so there you require this kind of systems to integrate those different sensors and to make sensor fusion possible. Simultaneous localization and mapping also possible with the help of this. Okay, so it is consume low power. Okay, and so suitable, making is suitable for battery power robots and UAVs. Okay, so unarmed aerial vehicles also. Sustainable AI driven robotics. Okay, support for AI ML framework. So it is PyTorch, TensorFlow, ROS is supported by this ONX, supported by this Jetson Orin Nano, and reinforcement learning based. Basically, it consists of ARM architecture. So that's why it is compatible with this these kind of operating system. Okay, so basically useful for machine learning and advanced deep learning models. Okay, so generative AI. So it is also used for generative AI, LLM driven robotic assistance and speech to action, vision to action models for interactive robotics. So like that, you can read this blog also, which I wrote in the Medium. Now we will talk about some control algorithms. So as you know that neural network. So what is neural network? So basically artificial neural network. So uh, it is neural networks basically used for to mimic the human brain. So billions of neurons are there. Okay, so we made some artificial, on the base of human brain, we made some artificial neural network system. Scientists made that ANN based systems, and then those uh, okay, so as you already know this neural network architecture. So basically input layer, then okay, mid layer, then output layer. Okay, so in mid layer there are different transformations. Okay, so how we are sending the data input to the neurons and how it is going to function. Then once it is going to function, then feed forward propagation, then uh, finding the loss at the output layer, where we are going to find out the loss between actual output and the predicted output. And as you know that every layer consists of weights and biases attached to that, and initially the weight are random. Then every training, every iteration, when we are going to feed forward directions, all weights and biases we are having initially, then it is going to optimize with the help of gradient descent algorithm also. So initially, like a U kind of shape, this parabolic upward parabola curve of gradient descent algorithm. So initially the weights are high, then it is slowly going to converge and reaching to the global minima. Okay, what is global minima? So loss function basically. What is loss function? So at the output of the neural network model, there is actual output. There is a difference between actual output and a predicted output. That is our basically loss, or you can say error also. So we are going to minimize those this error in every iteration. So when we are giving input to the input layer, then mid layer, then it is going to output layer, and then we are getting some outputs, and then actual output we are get, and there is predicted output. Actual output is there, and we are having some predicted output. So there is a always computation of loss or error between the actual output and the predicted output. And once we are able to find out that loss, we are going to differentiate this, partial differentiate this, and we are going to update all the weights. We are again moving in the backward direction, and we are going to update all the weights and the biases. So okay, so in every iteration we go to the forward propagation, computation of loss or error, mean square error, or based upon different scenario, computation of errors or loss. Then we are going to calculate that loss, then we are going getting this uh, loss, and we are finding the partial derivative of that loss function with respect of the biases and with respect of the weights, del L upon del W, del L upon del B biases, and weights W. Okay, so in the every process, when we go to the back propagation side and updates, continuous updation of weights and biases, we are getting the new weights. Every iteration we are getting the new weights. So in the same manner, neural network is getting trained, and with the help of optimization algorithm, it is going to reach the mid local minima. And okay, so our objective is to reach the global minima or local minima there. Okay, so that's then we can say that our convergence is done. Okay, so initially the curve is upward parabola and our weights are higher, so we slowly we are reach. Okay, so if we will move converge very fast, long distance, then this maybe in that process we are not able to reach our global minima. So that is one uh, problem of learning rate. So if we will keep our learning rate in neural network very high, in that case we are not able to reach our global minima, local minima easily. And on the other side, if we take our learning rate slow, for example in our Python code, when we are applying the neural network model uh, for the control strategy. So if we take our learning rate very slow, then it is going to converge but very slow. So it will take a huge amount of time. Maybe it will take 1 day, 2 day, like that. So when as per based on the program, so like that also. So this SMA based program definitely required more slow convergence. Why? Because better training, better neural network training, so that optimum and better convergence. If we can say better convergence, so we can say that neural network is trained better. Okay, so and now we are not using the simple neural network, we will use the adaptive neural network. So adaptive control is neural networks can adapt to change into the system dynamics or environment. They can be integrated into adaptive control frameworks where the network updates its parameters in the real time based on the new data, maintaining optimal performance despite variations. Okay, so every in the real time it is going to change, and as per the conditional different condition of the actuator motions, it this adaptive neural network controllers is going to adapt new variations. That's why simple neural network maybe fail, and maybe adaptive neural network control is highly required in this kind of scenario where we are dealing with the SMA based robots. Okay, so while okay, so uh, as I told you, neural network feed forward neural network, then computation of loss, then uh, that partial differentiation of loss vector with respect of weights and biases, and then uh, chain rule we applied, and we are getting the new weights and biases for in every iteration. So in that process, in training process, ultimately we are able to reach to the perfect weights and perfect biases. Okay, so which we can say that these are the fine tuning with the model. These are the fine tuned parameters. So those are the fine. So it's required a huge training and slow convergence. So that's why we take that learning rate very slow. So that's why this SMA based uh, training required a huge amount of time. So this is one more one control strategy: adaptive neural network control, then reinforcement learning control, then model predictive control. Okay, so MPC as a predictive control that forecast future states of the system. This allows for the better optimization of control inputs over a prediction horizon, accommodating constraints and improving performance. Okay, so these are some different control strategies. Okay, so fault detection and diagnosis, hybrid control systems, and okay, so PID with another systems, and then simulation and virtual. So basically, we will talk about reinforcement learning. So as you people already know that what is reinforcement learning. So we are having some agent and environment, and agent is based upon environment. He's going to take some actions, and based upon actions he's getting some reward or penalty. Okay, so for example, if we talk about autonomous vehicles, so autonomous vehicles, driverless vehicles where there's no need of drivers, in that case okay, so based upon the environment, so our environment may be our map of the uh, track where this driverless vehicle is moving. Okay, so in that case, our agent, our car is taking the decisions based on reinforcement learning algorithms. Okay, so if, for example, if this car needs to go in the forward direction, then he has to take left direction, and then he's to take another directions, like that. So whenever this car is moving, work taking actions, okay, so moving, in that case it is, for example, from the next stop he need to take left. So okay, so if he's going, if he reach that next stop, and if he's going in the wrong direction, for example, it is instead of left it is taking right directions, so immediately it is getting the negative penalty. Reinforcement learning controller are getting the negative penalty. So this reinforcement learning with the help of reinforcement learning algorithm, agent remember that next time if he will take in this stop, if he will take right motion, right direction, or maybe forward direction, both are negatively rewarded. So penalty is given to them, given to him. Instead, when he is taking left, so reward is given to him. So based upon this negative penalty and reward system, so he remember that whenever he is crossing this stop, he need to take left. So in that manner, he is training itself. Its controller is getting to training itself, and so okay, so after several huge effort or long training, this reinforcement based controller is able to understand whether he has to take what kind of decision he has to take, whether he has to take left or right, or in that particular stoppage. So like that, autonomous vehicle is moving in the particular track, and getting the information of all the motions, all the actions he has to take, all the correct actions. Because whenever he's getting the negative actions, he's getting the negative penalty. Okay, so this controller is designed in such a manner so that he's in the next iteration he's avoiding that negative penalty. He remembers that in the last step I taken this right motion, so I got negative penalty. So he's not repeating those tasks again. So in that motion, in that kind of scenario, it is training itself multiple iteration, maybe 10 days, 15 days. Once it is getting trained perfectly, then we can say that now the controller is perfectly to deploy. Okay, so like that, this reinforcement kind of scenario is there. So this is
Yeah,
very important.
Dr. Vishwanath, sorry for interrupt. I think time is going
Yeah,
completely. Yeah,
yes, Professor. So
please.
okay. So now the time is over.
Ah,
Oh, sorry, Professor.
ah,
I for. Okay, so okay, so these are some advanced controllers for the reinforcement learning based control. Okay, so professor, so I think I am almost done. Okay,
Yeah,
so almost done. I am all this is not required CNN based algorithms. Then generative AI. Okay, so I am showing something.
yeah, yeah,
Just 2 minutes only. Okay,
yeah,
generative AI, nowadays GPT transformers are there. So it is CNN. Okay, so conventional CNN are failed in the like struggle to understand long range dependencies. Then see. Okay, so then this long term dependency is removed by the RNN, recurrent neural network. Then after that LSTMs also remove these problems. Okay, so nowadays most important which I want to show you, this transformer models. So transformer models is basically on encoder decoder architecture. So it is it is removing all, it is capable of parallel processing, so highly advanced. It is able to highly advanced, so able to process many inputs together, parallel processing, which was earlier not present in LSTM architecture or GRU architecture or RNN architecture. So I suggest all the students, those who are students here, I suggest then try the, if you want a novelty in your control algorithms, so you can apply this transformer level architectures for your control strategy of the actuators or whatever you are doing. So okay, so this is the breakthrough research in attention all you need, by written by Asis Vaswani, Indian, who was working in Google. Okay, so I cannot. Okay, so many slides. Okay, so I will not talk about this. So thank you so much, Professor. So thank you giving me some wonderful opportunity to share my useful insight with
yeah. I should say thank
participants.
you. You are accepted my request.
Okay, so
Yeah,
participant, if you have any questions, so
yeah. Participants,
I
if
would
you
be
have any
happy.
questions, yeah, please. You can switch on your mic and you can discuss.
Hello,
Sir,
sir.
I
Good
got
evening,
one
sir.
question.
Yeah, please.
Yes,
One by one, please.
Hello,
yes, Professor.
hello, sir. Myself Kiran Kumar from
Yeah,
Keetham.
yes, yes,
Sir, may I know, like you have shown that SMA actuator,
yes.
whether it is available or it is made by you?
Yes, sir. Actually, in our lab, we used to buy several SMA wires and different SMA material, different size, shape. With the help of those wires and shapes, and we are thinking some design, and we are creating those design. Suppose I want twisted kind of motion, so we are making that arrangement in our lab with the help of, by doing ourselves only. So nobody is doing for us. We are testing different scenario by ourselves, and then we are using those things.
And how much
Sir,
low it is
one more
capable.
question, sir. Sir, are you working in a deep reinforcement learning in robotics, sir?
Yes. I worked actually. My I Ravi sir know my, actually earlier my research area was totally human biomechanics, where I worked on
No,
human
actually,
activity
he is
prediction.
working on robotics only, but he
Okay.
got the postdoc
Ah, then
opportunity in
then I
Mumbai
worked.
University.
ah,
Then he
then
went
I
there.
Sir,
worked
He,
in
because
material kind of works field, and then this SMA robots. Nowadays, I am working in computer science and artificial intelligence. Now applying algorithms, basically now applying algorithm on actuators nowadays.
okay.
So different gone
Yeah.
through phases. I also gone through. So in
Okay.
India, this is very difficult. So somebody
Mm.
get easily, somebody is not able to get. So we are facing
yeah.
also
Yeah, because
like that.
yeah, I'm working in this one area that I have some like doubts in that, so I don't know whom to meet. I'm searching for the experts or support
Sir,
from in this area.
Uh,
So
sir,
tomorrow, one more professor will give the lecture, Dr. Vijay Bhaskar.
okay,
He is also working that mission learning, deep learning algorithms.
yeah, and one more,
Vishwan,
yeah,
Vishwanath, is
one
it
more.
correct?
Yeah,
yes,
yes. He's also my guide also, and he's from
Ah,
NIT Bhopal. And
ah,
one more thing, if you want to discuss, okay, I am nowadays, luckily by the God grace, I am having also international contacts. So
ah,
anybody who want to contact with me, I shared my Gmail ID. So my
yeah,
name is Viswanath Bijlawan. You can search also in Google, and you can find out. So now my
yes, sir.
friend
Yeah.
is in University of
Mm,
Bristol, UK. He's a professor there. So
mm.
he is very nice guy, and we are having a lot of team with me. Like several students are working in advanced AI algorithms, and somebody is doing in KAIST also in Korea, top
yeah,
level
okay.
institutes. So we will have giant networks, so we can help each other. So yes, so definitely I will be happy if you can share your
Okay, sir. Thank you,
yes.
sir. Thank you very much. That very much needed
Thank you,
for
sir.
me, and thank you, sir. I'll
And I am
contact you.
very thankful for Ravi Kumar Mandava sir. So definitely
No,
he given me platform so today to speak. So
no,
I am very new to this talk kind of thing. So
no.
this may
Actually, I
maybe
know your
second or
profile.
third talk.
Actually,
So
I know your profile. Actually, we have good connection,
yeah,
and
yeah,
you make me that Engshim also in contact. Yeah,
yeah,
thank you.
Professor, definitely.
Yeah, yeah,
And I am also learning from you also, Professor. I saw
yeah,
your research, a very high level
yeah,
research. So
yeah.
yeah,
Yeah, from this, I'm going to
Hello,
conclude
sir.
today's session. Yeah, yeah, please, please, please. Yeah, please.
yeah,
Sir,
yes.
you mentioned that SMA is used in the stents implantation, right, sir?
Instant,
Yeah.
implantation. Yes,
So I have a doubt, sir. If we
yes.
put uh, in the artery, it is very
Hmm.
sensitive area.
Huh.
So when we how can be heated, sir? It is very
Yeah, yeah.
sensitive, right?
Actually, that
So
was
how the
suggested some year before. So it is very good working in for the dental implants. But nowadays, I don't know. But somebody made the design for the stents also. So I am not sure it is really easy to implant. But
Yeah,
yeah, as per the experts, they made this design. So yeah, I not made
actually,
this design, but I am
yeah,
suggesting that
actually,
it
he
can be
didn't
worked.
work, but he's telling that there is an opportunity to work in that area.
Actually, there are several actuators also
Yeah,
available now. So nowadays, different every year it is going to modify. So if we are able to modify those things, so we can make the use of those kind of stents also. Yeah,
so sir and one more, sir. So this SMA, how much weight it can sustain, sir? Is
it can. Huh? Yeah. It's a
it
very
depends
noble
on
question.
thickness or how
Sir,
much?
actually, when I tested this in my, I am saying my practical experience. So when I tested it in my lab, so as I show you that water can, so maybe 300, 350 grams, something like that. So easily it can sustain. So not only one SMA, you have to make, if you want to make a artificial muscle, so you have to make several arrangement of those kind of actuators, so that cumulative force you can generate, and then you can able to do your specific task. So 350 gram to 400 gram I tested by myself. So I am not sure, maybe other scientists maybe tested for high forces, they generated maybe high forces, because all things are based on the design itself. If you are able to make a specific design, so it will be helpful for you. It is generating more force.
So where can I get this material, sir?
Yeah, it is available, sir. It is available in the, I think, India Mart, and in Korea, sir. We used to make order from the China also, Chinese site also. For India Mart also, I think available. You can search in India Mart. You can definitely, you are able to find out. So basically, you ask your professor to purchase this for your lab, na. So because it's costly, 4,000, 5,000 for one bundles, and maybe that diameter is not working for you suitably. So different diameters wire you required for your SMA actuators.
yeah,
Thank you so much, sir. Very informative session.
Thank you, sir. Thank you. You like that. Thank you.
yeah. Thank you, Dr. Vishwanath. I'm very happy. Yeah, I think your lecture was very nice. I think people they are happy. They have enjoyed your
Okay,
session.
so that will be great, sir. If
Yeah,
people are happy, so thank you. I'm
yeah, they
very
are
happy.
enjoyed. I think I was also there entire your session.
Okay, sir. Okay.
Vishwanath sir, I have one question. Sir,
Yes, sir.
I have read many of the papers, and I have met with doctors. I mean, the experts from the people, those who are working with the microsurgery in case of actuator,
Yes,
the
sir.
IPMC they usually prefer. IPMC, ionic polymer, in place of SMA. And sir, is there
Okay.
any basic difference between that SMA is actually implemented for lifting a heavy load, or it can also go for very micro or very lightweight? If we think for any microsurgery, if I think of a robotic
Mhm.
microsurgery with the
Mhm.
actuators, and in that case, can we prefer SMA? Is it
Yeah, it's a
possible?
very great question. So really great question. So it is really challenging also, na. So whenever we are working on SMA, so really it's, we cannot say. So we have to test all the scenarios, and some scientists also claim that they successfully okay, so they are successfully able to make that possible. But when I tested, basically I found one major problem with this SMA. This is non-hysteresis curves. No, it's also non-linear, and its recovery is in slow motion and sometimes suddenly fast. So controlling action is very difficult to achieve this. So when I talk about force, so as I told you, I achieved 350 or 400 grams of maximum with the help of this one actuators. So I cannot say, I'm not sure about this, but your question is very genuine, and definitely I will also search for that also.
No,
If
sir, actually your presentation is so impressive. I was thinking of taking cup of tea, but I forgot to take that tea. I
Yeah.
thought that that will be taken later on. Let me complete this. So it was really kind of attraction, magnetic attraction was there, but I let it go. So go tea, you go. So let me take this first, because this is once in a life I might be getting, but might not be possible for me to get it for the second time. So that's why I asked these questions, because I was having a confusion that SMA, if there is a lagging, there is a question of lagging when it is coming to deformation to the original positions. If there is a time lagging, is there any alternative, sir, you have found while going through the research, that if in case, now this is a research gap we are finding, that is kind of in case of SMA, the deformation time, it is there is a delay, so there is a lagging. So in that case,
yeah.
in case of this PID controller, sir, if we difference PID, so it differentiative part, if we can make some changes, so it can rise, so it can also change the transient time. So there we can also control this lagging time. So is there any possibilities of with these things when it is
So
coming back to
maybe
the original
uh,
position?
your question is very typical. So
Yeah.
maybe I will answer that. If you can write mail, definitely I will
Yeah.
search for
Sure,
that, and
sure. I
I
have
will try
taken
to
your mail,
answer.
sir. I will write you positively. I will
Please,
write you.
please,
I
sir,
will try
please
to
write
find
me for.
solution. Then I also contact you positively.
Yes,
Yeah.
yes, definitely.
Thank
And
you
if
very
you are
much for
also
the
interested,
presentation, sir.
if
Yeah.
any
And thank you,
participant
Ravi
also
sir,
interested,
for
Yeah.
requesting Viswanathan sir for coming and giving this
Yeah.
outstanding presentation to us. Thank you very
Yeah.
much.
Thank you. Thank you.
thank you,
Thank
sir.
you.
Thank you for
Yeah.
wonderful
I
words.
I have one request, Dr. Vishwanath. People are asking your presentation. Can I share?